In the beginning of the scientific revolution, humanity looked to the heavens and began to ask questions that would forever change our understanding of the universe. It was a time when the world was still wrapped in mystery, and the forces that governed motion, matter, and light seemed almost divine. For centuries, humankind had tried to make sense of the cosmos through philosophy and intuition, but something new was beginning to take shape, a movement driven not by belief, but by observation, logic, and mathematics. This was the dawn of classical physics, a framework that would soon become the foundation of modern science. It began with curiosity and transformed into a powerful language that could describe how everything in the universe moved and interacted. At the heart of this revolution was a handful of thinkers whose ideas would echo across centuries. Galileo Galilei, often called the father of modern science, dared to challenge the long-standing dogmas of the ancient world. By rolling balls down inclined planes and measuring their motion, Galileo uncovered a hidden simplicity in nature. He saw that objects accelerate uniformly when falling and that their motion could be predicted using mathematical laws. The universe, he realized, was not a realm of chaos but of order. Every falling apple, every swinging pendulum, obeyed the same principles. This discovery marked a turning point. Nature could be understood not through guesswork or faith, but through precise measurement and reason. A few decades later, Isaac Newton took these early insights and forged them into something far greater, a universal theory of motion. In 1687, Newton published Philosophiae Naturalis Principia Mathematica, a masterpiece that would define physics for more than 2 centuries. Within its pages lay 3 laws of motion and a universal law of gravitation that could explain everything from the fall of an apple to the orbit of the moon. Newton's mathematics united heaven and earth under a single framework. For the first time in history, humanity possessed equations that could predict the future behavior of matter. The cosmos was no longer a mystery, it was a vast, precise machine governed by laws that never failed. To Newton and his followers, the universe resembled a perfectly wound clock. Every planet, every star, every atom moved according to fixed rules. If one knew the initial conditions, the position and velocity of every particle, then, in theory, one could calculate the future of the universe itself. This idea became known as determinism, and it dominated scientific thought for centuries. It painted a world of perfect predictability, where chance and uncertainty had no place. The motion of the planets, the flight of cannonballs, the path of comets, all could be reduced to elegant formulas. This vision of the universe as a grand, orderly mechanism inspired generations of scientists, engineers, and philosophers. But classical physics was not just about gravity and motion. It also sought to understand the invisible forces that filled the space around us. In the 18th and 19th centuries, as Newton's ideas spread through Europe, new questions arose. What was light? How did electricity and magnetism work? Could heat be explained by the same laws that governed motion? These questions drove physicists deeper into the heart of matter and energy, leading to discoveries that seemed to confirm the power and completeness of the classical worldview. One of the key figures in this new chapter was James Clerk Maxwell, a Scottish physicist whose equations would forever change our understanding of light and electromagnetism. Building on the work of Faraday and others, Maxwell unified electricity, magnetism, and light into a single theory, a grand synthesis showing that light itself was an electromagnetic wave. His equations described how electric and magnetic fields propagate through space, interacting with each other in perfect harmony. It was one of the most beautiful and elegant achievements in science. For the first time, scientists could explain lightning, magnets, and the rainbow under one theoretical roof. The triumph of classical physics seemed complete. By the late 19th century, confidence in this framework was absolute. Scientists believed they were on the verge of a final understanding of nature. Lord Kelvin famously declared that physics was nearly complete, save for a few clouds on the horizon, minor anomalies that he believed would soon be resolved. The laws of motion, thermodynamics, and electromagnetism appeared to explain everything from the planets in orbit to the vibrations of a violin string. In laboratories across Europe, precision instruments confirmed the predictions of theory again and again. The age of certainty had arrived. The universe was a vast, predictable engine, and humanity had finally discovered its blueprints. Yet, even as the world celebrated this triumph, subtle cracks began to appear. Nature, it seemed, was not as mechanical as it appeared. As scientists looked more closely into the behavior of atoms, light, and energy, they began to find inconsistencies that could not be explained away. Experiments produced results that defied the old equations, hinting at a hidden world that operated by different rules. These were the first whispers of a coming revolution, though few recognized them at the time. One of those troubling mysteries involved the nature of light itself. For centuries, physicists had debated whether light was made of particles or waves. Newton had argued that it consisted of tiny corpuscles, while others, like Huygens, believed it was a wave that traveled through an invisible medium called the ether. By the 19th century, experiments such as Thomas Young's double-slit test seemed to confirm the wave theory. Light produced interference patterns just like ripples on water. Maxwell's equations, too, supported the wave picture, describing light as oscillating electric and magnetic fields. The debate appeared settled until new experiments began to challenge this certainty. At the same time, other branches of physics were uncovering strange behavior in the microscopic world. Thermodynamics, the science of heat and energy, had revealed deep relationships between motion, temperature, and work. Scientists like Rudolf Clausius and Ludwig Boltzmann developed the concept of entropy, the measure of disorder in a system, and showed how the second law of thermodynamics governed the direction of time itself. But when they applied these ideas to individual atoms, contradictions emerged. Classical physics could not fully explain how energy was distributed among particles, nor why objects emitted light at certain colors when heated. The ultraviolet catastrophe, as it came to be called, was one of those small clouds that refused to disappear. It was in this landscape of triumph and confusion that Max Planck would emerge. But before his breakthrough, the stage had to be set by centuries of progress and belief in the classical order. The world of the 19th century was defined by the confidence that reason and mathematics could explain all things. Engineers used Newton's laws to build railways, bridges, and machines with astonishing precision. Astronomers used them to predict eclipses decades in advance. Physicists used Maxwell's equations to develop telegraphs, electric motors, and the first light bulbs. Humanity had harnessed nature, bending it to its will through science. It seemed that there was no mystery left to uncover, and yet, beneath the surface, nature was preparing to reveal a secret that would shatter this beautiful illusion. The deeper scientists probed into the structure of matter, the more it resisted explanation. Atoms, once thought to be solid and indivisible, began to reveal strange internal structures. Electrons, discovered by J. Thomson in 1897, behaved in ways no classical model could predict. Theories of heat radiation failed to match experimental data. Light sometimes acted like a wave, sometimes like a stream of particles, depending on how it was observed. The deterministic universe of Newton and Maxwell was beginning to tremble. To understand how revolutionary this change would be, one must grasp the philosophical power of classical physics. It was not just a collection of equations, it was a worldview, a belief that the universe was governed by absolute, continuous laws. Space and time were thought to be infinite and unchanging, a rigid stage upon which matter danced in perfect mathematical harmony. Every event had a cause, and every cause produced an effect. There was no room for chance, no room for uncertainty. This vision shaped not only science but also philosophy, art, and even politics. It gave rise to an age of industry and progress, a belief that through reason and technology, humanity could master nature completely. But in the laboratories of Berlin, Vienna, and Paris, a quiet unease began to spread. The equations that had once seemed unshakable were failing to predict reality. As scientists measured the spectrum of light emitted by hot objects, the results stubbornly refused to match the predictions of classical theory. According to Maxwell's and Boltzmann's calculations, as an object was heated, it should emit infinite energy in the ultraviolet range, a clear impossibility. Yet the data could not be ignored. Something fundamental was missing from the old physics, something that no amount of mathematical adjustment could fix. In those years, the spirit of inquiry was intense. Universities were alive with debate, and physicists were pushing their theories to the limit. They had built a magnificent structure of knowledge, but it was becoming clear that its foundations might not be as solid as once believed. The equations worked beautifully for large objects and ordinary conditions, but as the focus turned toward the atomic scale, their reliability dissolved. The machinery of the classical universe began to break down when examined too closely. The more scientists tried to peer into the heart of matter, the stranger it became. This was the paradox of classical physics. It was both immensely powerful and profoundly limited. It could send rockets into the sky and predict the movement of the planets, yet it could not explain the simple glow of a heated metal or the way atoms absorbed and released energy. The laws that had ruled for centuries seemed to stop working at the smallest scales of nature. The clockwork universe was no longer ticking as smoothly as once believed. By the end of the 19th century, science stood at a crossroads. On one path lay the continuation of classical thought, a belief that with enough refinement, all mysteries could be solved within the existing framework. On the other lay the unknown, a world that behaved according to rules no one had yet imagined. The air was thick with both pride and tension. The achievements of Newton, Maxwell, and others were undeniable, but so too were the strange anomalies that defied explanation. The universe was whispering a new language, one that only a daring mind could learn to interpret. Max Planck would become that mind, but before his revolution could begin, the world had to feel the weight of its own certainty. The conviction that everything was already known, for it is only when the boundaries of knowledge are tested that true discovery becomes possible. Classical physics, in all its glory, had reached its limits. The age of certainty was ending, and a new, mysterious frontier was about to unfold, a frontier that would reveal a universe far stranger, deeper, and more beautiful than anyone had ever dreamed. As the 19th century drew toward its close, physics stood like a towering cathedral of logic. Every pillar, from Newton's laws to Maxwell's waves, seemed perfectly placed. The air of triumph was intoxicating. Laboratories across Europe glowed with the soft light of new discoveries, spectroscopes splitting beams of color, cathode rays flickering in glass tubes, delicate instruments measuring forces so faint they seemed almost spiritual. The world believed that the final chapter of science was already written. But nature, always a step ahead of human certainty, was preparing to reveal a hidden script that would change everything. The first sign came from experiments so simple that few realized their importance. When metals were heated, they glowed, first red, then orange, then white. Every craftsman had seen it, every blacksmith knew the pattern by heart. Yet when physicists tried to calculate the exact relationship between color and temperature, their equations failed. According to classical theory, the energy radiated by a hot object should rise endlessly as the wavelength of light grew shorter. The result was absurd, infinite energy at ultraviolet frequencies. Reality, of course, did not behave that way. No furnace, no star, no object in the universe emitted infinite radiation. But the mathematics of classical physics insisted that it should. This contradiction, subtle but undeniable, became a wound that deepened with every attempt to heal it. Some physicists tried to patch the theory with complex assumptions. Others ignored the anomaly, convinced it would fade with time. Yet the problem only grew more stubborn. The deeper scientists looked, the clearer it became that the laws that worked so beautifully for planets and pendulums failed in the atomic realm. It was as though the universe played by two different sets of rules, one for the grand stage of the cosmos, and another for the invisible world within. The harmony that Newton had imagined began to sound dissonant. In those days, Berlin was one of the intellectual capitals of Europe. Inside its universities and institutes, some of the greatest minds of the age wrestled with these paradoxes. Among them was a quiet, methodical man named Max Planck. Born in 1858 in Kiel, Germany, Planck had been raised in an atmosphere of discipline, faith, and intellectual rigor. His teachers had warned him that physics was nearly finished, that only a few small problems remained to be solved, but Planck was not seeking fame or revolution. He simply wanted truth expressed in the language of mathematics. For years, he studied thermodynamics, the laws governing heat, energy, and entropy, searching for a deeper unity beneath them. What he found instead was the first crack in the great edifice of classical thought. Planck's problem was deceptively simple: to describe how objects emit radiation as they are heated. He worked tirelessly, comparing theory with data collected by meticulous experimenters. Every known equation failed. The numbers refused to align, defying the logic of centuries. And then, one evening in 1900, Planck made a decision that would alter the history of science. He introduced an idea so strange, so radical, that even he could scarcely believe it. Perhaps, he thought, energy does not flow continuously. Perhaps it comes in small, indivisible packets, each one a discrete quantum. He did not yet understand what this meant physically. It was, at first, a mathematical trick, a desperate attempt to fit the curve of data. But the trick worked. The results matched perfectly. Nature, it seemed, agreed. The implications of this success were staggering. If energy was truly quantized, then the smooth, continuous picture of the universe painted by Newton and Maxwell was incomplete. The fundamental fabric of reality was not a seamless continuum, but a mosaic of tiny steps, discrete and indivisible. Yet Planck was cautious. He published his results modestly, without grand claims. He regarded his discovery as a temporary fix, not a revolution. Few of his peers paid much attention. The world of physics moved on, unaware that it had just crossed the threshold into a new age. But the cracks in classical theory continued to widen. In 1905, a young patent clerk named Albert Einstein took Planck's quantum assumption and used it to explain another mystery: the photoelectric effect. When light shines on certain metals, it can knock electrons loose, creating an electric current. Classical physics predicted that the brightness of light should determine the energy of these electrons. But experiments showed otherwise. Only the frequency mattered. Einstein proposed that light itself was made of quanta, later called photons, and that each photon carried energy proportional to its frequency. With this, the dual nature of light was born: wave and particle, continuous and discrete, existing in a tension that defied classical logic. Einstein's proposal was audacious, almost heretical. The wave theory of light had reigned supreme for nearly a century, supported by experiment after experiment. Yet his idea explained the data perfectly. Planck's quantum had escaped the pages of theory and entered the real world. Slowly, reluctantly, the scientific community began to realize that something profound was unfolding. The old physics, with all its precision and beauty, could no longer describe the strange behavior of light and matter. Still, the classical mindset was not easily abandoned. Many clung to the comfort of determinism, the belief that the universe was governed by strict, predictable laws. It was a view deeply woven into the fabric of 19th-century thought, a symbol of order in an industrial age that worshipped progress and control. But nature had never promised to be simple. As new experiments probed deeper into the atom, the contradictions multiplied. Electrons refused to obey the equations of classical electromagnetism. Their motion within atoms produced spectra, sharp lines of color, that could not be explained by any continuous model. Each line represented a precise amount of energy absorbed or emitted, as if the electrons leapt between invisible steps. The logic of the old world was collapsing. To the generation that had grown up under Newton's shadow, this was deeply unsettling. The deterministic machine that had once explained the heavens was losing its gears. What replaced it was something ghostly and unpredictable. The boundaries between certainty and probability began to blur. A new kind of physics was being born, one that demanded not just new equations, but a new way of thinking about reality itself. It was the beginning of quantum mechanics, though the name had not yet been coined. Looking back, one can see how the rise of classical physics made this transformation both inevitable and extraordinary. Each success of the old theories brought scientists closer to the edge of discovery, until the framework itself could no longer contain the truth it sought to describe. The very precision that had made classical physics so powerful became its weakness. It assumed continuity where there was discreteness, certainty where there was chance. The limits of Newton and Maxwell were not failures but signposts pointing toward a deeper order. A universe ruled not by rigid predictability but by probabilities, possibilities, and the delicate interplay of observation and reality. Yet even as the new century opened, the spirit of classical physics refused to die. Its influence endured in the way scientists thought, the way engineers built, the way philosophers spoke of truth. The deterministic vision had shaped human culture for generations. The idea that the future could be predicted, that every effect had a cause, gave rise to the engines of industry, the planning of cities, the rhythm of progress. It was more than a theory, it was a worldview. And now that worldview was unraveling. As the 20th century advanced, the tension between the old and new grew sharper. Experiments in atomic structure, in blackbody radiation, and in the emission of light all pointed to the same conclusion: the classical laws were only approximations, shadows of a deeper, hidden reality. The universe was not a perfect machine, but a symphony of probabilities, vibrating at the edge of comprehension. Planck's constant, a tiny number that measured the size of those energy quanta, became the key to this new realm. It was as though nature whispered through that constant, revealing that continuity itself was an illusion. To the philosophers of the Enlightenment, this would have been unthinkable. They had believed in the absolute power of reason, in a cosmos that could be mastered through mathematics. But the quantum world mocked that dream. It showed that even with perfect knowledge, the future could never be predicted with certainty. Reality itself was indeterminate until observed. The act of measurement changed what was measured. In this strange new universe, the observer was no longer separate from the observed. Consciousness and matter were intertwined in a dance that defied classical understanding. And yet, in a strange way, the revolution completed the dream it destroyed. For by revealing the limits of classical physics, Planck and those who followed him expanded humanity's reach beyond imagination. They unlocked a universe richer and more mysterious than any clockwork could ever be. The equations of Newton had explained motion. Those of Maxwell had described light, but the equations born of Planck's quanta would describe the building blocks of existence itself. They would lead to technologies that harnessed the invisible, transistors, lasers, quantum computers, and to a new philosophy of nature, one that embraced uncertainty not as ignorance, but as truth. When we look back on the rise of classical physics, it is tempting to see it merely as a prelude to quantum mechanics, a stepping stone to greater things. But that view does it injustice. Classical physics was a triumph of the human spirit, a testament to reason and imagination. It gave us the tools to measure, to predict, to build. It taught us that nature speaks a language we can learn, even if we will never master it completely. Its limits do not diminish its greatness, they define it. For every theory, no matter how beautiful, eventually meets the frontier of the unknown, and it is at that frontier that discovery is born. In the quiet of his Berlin study, Max Planck could not have known the magnitude of what he had done. He had sought only to solve a minor problem in heat radiation, not to rewrite the laws of the universe. Yet his modest formula contained within it the seed of a revolution that would engulf all of physics. From that single idea would grow the theories of Einstein, Bohr, Heisenberg, Schrödinger, and countless others. The deterministic machine of Newton would give way to the quantum universe, strange, unpredictable, but exquisitely precise in its own way. The story of the rise and limits of classical physics is at its heart a story of human ambition. It tells how we reached for certainty and found mystery instead. It reminds us that knowledge is not a straight path but a spiral, winding ever deeper into the unknown. Each age believes it has found the truth, until the next reveals a deeper layer beneath. The physicists of the 19th century believed they were standing at the summit of understanding. In reality, they were standing at the edge of a vast, uncharted realm. Their confidence, their precision, and even their errors were all necessary steps toward a new vision of the cosmos. And so, as the curtain fell on the 19th century, the great cathedral of classical physics still stood, majestic, complete, yet trembling on its foundations. The clockwork universe had reached its final hour. In its place, a new dawn was breaking, one lit not by the steady glow of certainty, but by the flickering, probabilistic light of the quantum world. What began with Galileo's falling bodies and Newton's laws would soon transform into something infinitely stranger and infinitely more beautiful. A universe alive with possibilities, forever beyond the full grasp of prediction, yet always within reach of wonder. For centuries, humanity has been fascinated by light. It was the first thing to pierce the darkness of the unknown, the silent messenger of the heavens. From the flickering flame of a candle to the radiance of the sun, light has always been more than a mere phenomenon. It has been a symbol of truth itself. Yet, for all its familiarity, light has long refused to yield its deepest secrets. The story of how science came to understand its mysterious behavior is one of the most profound and beautiful chapters in human knowledge, stretching from the dawn of optics to the threshold of quantum theory. In the 17th century, when the modern scientific method was just taking shape, thinkers like Isaac Newton and Christian Huygens looked at light and saw two different worlds. Newton, with his precise experiments on reflection and refraction, believed that light was made of tiny particles, corpuscles, shot out from luminous bodies. His theory could explain many of light's behaviors: its straight line motion, its ability to cast sharp shadows, its reflection from mirrors. Huygens, on the other hand, imagined light as a wave propagating through an invisible medium called the ether. He saw interference and diffraction patterns as proof that light could bend and blend like ripples on water. For more than a century, these two visions clashed, and the mystery of light deepened. By the early 19th century, a young Englishman named Thomas Young performed a simple yet revolutionary experiment. He passed a beam of light through two narrow slits and observed the pattern that formed on a screen behind them. To his astonishment, it was not the pattern one would expect from particles, but a series of bright and dark fringes, interference, pure and unmistakable. Where the crests of two waves met, the light brightened; where a crest met a trough, they canceled each other out. Light, it seemed, behaved exactly like a wave. Young's experiment should have ended the debate, but the mystery only grew. If light was a wave, through what did it travel? Sound moved through air, water waves through liquid, but space, the vast arena between Earth and stars, appeared empty. Scientists postulated an invisible substance filling all of space, the luminiferous ether, so tenuous that it could not be seen, touched, or measured, yet firm enough to carry the waves of light. It was a comforting idea, one that preserved the logic of the time. Every effect must have a medium. Then came James Clerk Maxwell, whose genius united electricity, magnetism, and light into a single grand theory. With a set of 4 equations, he revealed that changing electric and magnetic fields could sustain one another and travel through space as waves. When he calculated their speed, it matched perfectly the measured speed of light. The conclusion was breathtaking. Light was an electromagnetic wave. For the first time, its nature had a mathematical home. Yet, in Maxwell's view, these waves still needed a stage upon which to move, the ether. The question of what this ether was became one of the great puzzles of the 19th century. In 1887, Albert Michelson and Edward Morley set out to detect the Earth's motion through the ether. They built an exquisitely sensitive interferometer to measure the speed of light in different directions, expecting to find small variations as the planet moved through the ether wind. To their shock, they found none. No matter how they turned the device, light's speed remained the same. The result was inexplicable. Either the Earth dragged the ether along with it in some magical way, or the ether did not exist at all. This was more than a technical problem. It was a crack in the foundation of classical physics. Light seemed to ignore the motion of the observer, defying every intuition about waves. The mystery deepened into something almost metaphysical. Around this time, other experiments began to reveal even stranger behaviors. When metals were heated, they emitted light that changed color with temperature, producing the black body spectrum that Planck would later study. When light struck certain substances, it could eject electrons, producing an electric current, the photoelectric effect. When gases were excited, they emitted light at sharply defined colors rather than a smooth rainbow. Each of these observations seemed to hint that light and energy were connected in ways no one had expected. The tidy equations of Maxwell could not fully explain them. It was as if nature were whispering that something deeper was at play, something hidden within the very essence of energy itself. For a while, scientists hoped that better measurements or more refined mathematics would restore order. But the more they looked, the stranger light became. It could interfere with itself, diffract around corners, and yet in other experiments it behaved like a stream of discrete impacts. In the photoelectric effect, for instance, increasing the brightness of light did not increase the energy of the emitted electrons, only the color, or frequency, mattered. That made no sense if light were purely a wave, for waves of greater amplitude should carry more energy. It was as though light carried its energy in packets, each linked to its color. Planck's quantum idea, introduced to explain the black body spectrum, offered a tantalizing clue. Perhaps energy, even in light, came in tiny quanta. The wave-particle mystery was about to unfold. To appreciate the strangeness of this, one must understand how revolutionary the idea was. For generations, scientists had built their worldview on continuity. Energy could vary smoothly, matter could be divided endlessly in theory. The notion that nature came in indivisible chunks contradicted everything classical physics stood for. Yet the experiments would not be silenced. When light struck metal, electrons were ejected instantly, no delay, no gradual buildup as one might expect from a continuous wave. Only photons with energy above a certain threshold could dislodge them. Below that frequency, no electrons emerged, no matter how intense the light. The conclusion was unavoidable. Light behaved as if it consisted of discrete particles, each carrying a quantum of energy equal to its frequency multiplied by Planck's constant. Einstein's explanation of this phenomenon in 1905 was both brilliant and unsettling. It preserved the mathematics of Planck's formula, but stripped it of its modesty. Where Planck had viewed quantization as a mathematical convenience, Einstein declared it a fundamental property of nature. Light itself was quantized. This was not just a tweak to existing theory, it was a revolution in the making. Suddenly, the familiar glow of sunlight, the warmth of a flame, the sparkle of a star, all were manifestations of individual quanta streaming through space, interacting with matter in jumps, not flows. Energy, that most continuous of concepts, had revealed its granular soul. Yet the wave aspect of light refused to die. Experiments with interference and diffraction continued to show patterns that only waves could produce. Physicists found themselves trapped between two contradictory truths. Light was both particle and wave. Neither description alone could capture its full behavior. It was as if nature demanded two languages, mutually exclusive yet jointly necessary. For the human mind, trained to choose one reality or the other, this duality was profoundly unsettling. For the universe, it was simply how things were. As the 20th century began, the study of light and energy became the crucible in which modern physics would be forged. Laboratories buzzed with new instruments capable of probing smaller scales and shorter times than ever before. Spectroscopy revealed the fingerprints of atoms in light, each element producing its unique spectral lines. When scientists tried to model these lines using classical mechanics, they failed completely. Electrons orbiting a nucleus should emit radiation continuously and spiral inward, yet atoms were stable. Something invisible was protecting them. It was as though energy could only be absorbed or emitted in certain fixed amounts. Quanta again, asserting their presence everywhere. Meanwhile, Planck continued to wrestle with the meaning of his own discovery. He had stumbled upon quantization as a necessity of mathematics, not as a vision of reality. The idea that nature itself might be discrete felt almost blasphemous to a man raised in the tradition of continuity. But the data were relentless. His constant, that small number linking energy and frequency, became the bridge between the old world and the new. Without intending it, he had lit the fuse of the quantum revolution. Einstein's work on light quanta, though initially doubted, soon found support from experiments on the Compton effect, where X-rays scattered from electrons as if they were billiard balls colliding. Yet even Einstein was uneasy with what this implied. Light, depending on how one observed it, could act as a particle or as a wave. It was both real and ghostly, localized and spread out, continuous and discrete. The old certainties of physics had dissolved into paradox. The deeper scientists explored the nature of light, the more mysterious it became. The early decades of the new century were marked by wonder and confusion. Every discovery about energy seemed to overturn another piece of the classical worldview. Heat, once understood as the vibration of particles, now seemed to involve discrete exchanges of quanta. Atoms, once imagined as miniature solar systems, were found to behave according to statistical laws that defied everyday logic. The mystery of light became a mirror, reflecting the mystery of reality itself. What was energy? Was it a continuous field, a collection of particles, or something beyond both, something that transcended human categories? No one could say for sure. And yet, from this confusion arose clarity of a new kind. Scientists began to realize that perhaps the problem lay not with light, but with our assumptions. The universe might not conform to human intuition at all. Instead of forcing nature into familiar molds, physicists started to build theories that accepted its strangeness. Energy and light were no longer seen as opposites of matter, but as different expressions of the same underlying reality. Einstein's equation, eta mc captured this unity elegantly. Energy and mass were interchangeable, two sides of one cosmic coin. Light could create matter, matter could dissolve into light. The boundaries blurred, and a new vision of the universe began to emerge. By the time the First World War ended, the mystery of light had become the central problem of physics. The next generation, Bohr, de Broglie, Heisenberg, Schrödinger, would take the clues left by Planck and Einstein and weave them into a new theory that defied all classical notions. But at this stage in the story, the world still stood on the edge of that transformation. The air was thick with uncertainty and anticipation. The laws of nature were about to be rewritten, and at the heart of it all burned the ancient, unyielding light, the same light that had guided humanity through darkness, now revealing not comfort, but the bewildering complexity of reality itself. As the 20th century inched closer, the scientific world stood poised between two realities, one defined by certainty, the other by confusion. The grand machinery of classical physics still ruled the visible universe, but under the microscope of new experiments, its foundations began to tremble. Light, the purest expression of nature's elegance, no longer behaved as expected. It shifted and shimmered, refusing to obey the mathematical laws that had once described it perfectly. This rebellion of nature wasn't loud or sudden, it was subtle, quiet, and persistent, a whisper of something deeper that human understanding had yet to grasp. The physicists of the late 19th century were determined to decode these mysteries. To them, light was both a wave and a symbol of progress, a phenomenon that could illuminate not just rooms and streets, but the truth itself. The work of James Clerk Maxwell had unified electricity and magnetism into a single grand theory, showing that light was a wave of electromagnetic energy. This revelation was considered the crown jewel of classical science. But soon after, experiments began to reveal inconsistencies that Maxwell's theory couldn't fully explain. Light acted like a wave, yes, but sometimes it behaved as though it were made of tiny particles. The very essence of its nature appeared to shift depending on how it was observed. This duality puzzled even the greatest scientific minds. Thomas Young's double-slit experiment had already shown that light could interfere with itself, producing delicate bands of brightness and shadow on a screen, proof of its wave-like nature. Yet, when scientists tried to measure how that interference occurred, the results seemed to vanish, as if light changed its behavior the moment humans tried to observe it too closely. It was almost as if the universe refused to give up its secrets easily, forcing humanity to rethink the nature of observation itself. The story of energy and light, however, extended beyond laboratory curiosities. It touched the very core of physics, challenging ideas that had seemed sacred for centuries. Classical physics had always assumed that energy could be divided infinitely, just like time or distance. A heated object, it was believed, should radiate energy continuously, its color changing smoothly as temperature increased. Yet when physicists studied the radiation of heated bodies, a strange pattern emerged. At lower frequencies, the predictions of classical theory matched perfectly with experimental data. But as the frequency increased, the calculations exploded to infinity. This impossible result became known as the ultraviolet catastrophe. It was here that Max Planck, a quiet German physicist working in Berlin, stepped into the scene. Planck wasn't a man searching for revolution. In fact, he had always considered himself a conservative thinker, deeply loyal to classical principles. But faced with the ultraviolet catastrophe, he realized something extraordinary had to change. In 1900, he proposed that energy was not continuous at all, it came in discrete packets, each one proportional to its frequency. These packets he called quanta. The idea was shocking, almost heretical. Planck himself hesitated to believe it fully. Yet the mathematics worked perfectly, explaining the experimental data for the first time. Unknowingly, Planck had cracked open a door that would lead physics into an entirely new realm. Behind it lay a world where energy, matter, and light followed strange, probabilistic rules. A universe where certainty dissolved into possibility. But before that revelation could take hold, others would have to test its meaning. Among them was Albert Einstein, a young patent clerk whose restless imagination saw connections where others saw confusion. Einstein took Planck's idea and pushed it even further. If energy came in quanta, perhaps light itself was made of discrete particles, later called photons. With this bold step, Einstein explained the photoelectric effect, a phenomenon where light striking a metal surface could knock electrons free. Classical wave theory couldn't account for why a light below a certain frequency, no matter how intense, failed to release any electrons. But when Einstein treated light as particles, the puzzle vanished. Only photons with enough energy could dislodge electrons, proving that energy was not continuous after all. For this discovery, Einstein would later win the Nobel Prize, not for relativity, but for helping prove Planck's revolutionary concept. Yet even as this new quantum picture emerged, it created discomfort among many scientists. The dual behavior of light, as both a wave and a particle, was too strange to accept easily. How could something be two contradictory things at once? For decades, physics had thrived on determinism. If one knew all the variables, one could predict everything. But now, uncertainty began to creep into the heart of science. Light no longer moved through space as a simple wave, it could appear and disappear, interact and transform, depending on how it was measured. The universe, it seemed, was weaving a tapestry of probabilities rather than certainties. In laboratories across Europe, experimental physicists tried to reconcile this chaos. They split beams of light, bent them through prisms, and measured their energies with instruments of unprecedented precision. Each experiment added a new layer to the mystery. Sometimes light behaved as expected, other times it defied logic entirely. The old equations were no longer enough. Something deeper was at work, a principle that governed the behavior of both waves and particles, uniting them in ways no one yet understood. The mysterious behavior of energy also showed itself in the atoms that made up matter. When gases were heated or electrified, they emitted light at specific colors or frequencies, forming unique spectral lines like fingerprints of each element. Classical theory could not explain why these lines existed, why atoms emitted only certain energies and not others. It was as though energy within atoms came in quantized steps, each corresponding to a precise amount of energy change. Planck's theory hinted at this, but it was Niels Bohr who would soon take that concept and apply it directly to the structure of the atom. Bohr's atomic model, introduced in 1913, borrowed Planck's quantum idea and gave it a physical home. He proposed that electrons could orbit the nucleus only at specific distances, each corresponding to a particular energy level. When an electron jumped from one level to another, it emitted or absorbed a quantum of light. This explained the spectral lines perfectly. Light was no longer a random glow, but a coded message from the quantum world. Each color, each frequency, told the story of an electron's journey between energy states. Through these revelations, humanity began to see that light was not just illumination, it was information. It carried the whispers of atoms, the signatures of stars, and the fingerprints of the universe itself. Every photon that reached the human eye or a telescope lens carried within it the history of its birth, a cosmic message written in quanta. But while these discoveries inspired wonder, they also deepened the philosophical crisis in physics. The universe appeared to be built on paradoxes. When unobserved, light could behave as a wave. When measured, it revealed its particle nature. This duality wasn't just a trick of perception, it was a fundamental aspect of reality. The same mystery extended to matter itself, as later experiments showed that electrons too could exhibit wave-like behavior. The border between particle and wave dissolved, and with it, the neat categories of classical physics. The story of light and energy had transformed from a tale of observation into a profound question about existence. What is reality, if its nature changes when we look at it? Does observation create the outcome? These were not questions physicists had ever expected to face, yet they became central to the new physics that was emerging. As years passed, quantum mechanics grew into a full-fledged theory, encompassing not only light but also matter, motion, and energy in every form. It explained how atoms bonded to form molecules, how electrons tunneled through barriers, and how particles interacted in ways no classical law could describe. Yet, at its core remained that same strange duality, the mysterious behavior of energy and light that had sparked it all. Modern technology would soon harness this mystery in unimaginable ways. The laser, for instance, works by controlling the emission of photons, quantized bursts of light energy that move in perfect synchrony. Quantum mechanics explained why semiconductors could regulate electric currents, paving the way for transistors, computers, and the digital age. From the glowing pixels on a smartphone to the beams of light guiding spacecraft across the solar system, every application was a tribute to the same strange behavior of light that once defied understanding. The philosophical implications of these discoveries reached far beyond physics. The deterministic vision of the universe, a machine governed by precise laws, gave way to a universe alive with probabilities. The simple notion of cause and effect had to be reimagined. Even the act of observing became a participant in reality, blurring the line between the observer and the observed. Light was no longer just an external phenomenon, it was part of the very structure of existence, intertwined with consciousness and measurement. And so, the journey that began with confusion ended with enlightenment. Not the certainty of answers, but the awareness of mystery. The behavior of energy and light had revealed that the universe was far more dynamic, intricate, and unpredictable than anyone had dared to dream. Each flicker of light in the cosmos, each burst of energy from a star, was a reminder of the delicate dance between order and chaos that defines reality itself. The scientists who first glimpsed this mystery could not have imagined how far it would reach. Their equations, their doubts, and their relentless curiosity became the foundation for technologies, philosophies, and ideas that continue to shape modern civilization. The story of light had come full circle, from a wave rippling through space to a quantum whisper from the fabric of the cosmos. In the end, the mysterious behavior of energy and light was not a failure of classical physics. It was an invitation. An invitation to look deeper, to question harder, and to accept that truth might come in forms beyond human intuition. Light, the symbol of clarity, had revealed the shadows beneath certainty. And in those shadows, humanity found a new kind of illumination. Not the light that dispels darkness, but the light that reveals mystery. In the final years of the 19th century, a quiet revolution was beginning to stir, not in the streets, but in the minds of scientists who were daring to question the nature of reality itself. In Berlin, a man sat surrounded by blackboards filled with equations, chalk dust gathering on his sleeves as he tried to make sense of the numbers that refused to behave. His name was Max Planck, a thinker of rare precision and humility, a man who sought order in a world that was beginning to reveal its chaos. He was not looking for fame or revolution. In fact, he distrusted both. All he wanted was to understand why nature's laws, so perfect in the macroscopic world, seemed to falter when they met the radiant dance of heat and light. The air of the scientific community was charged with optimism at that time. Physics, many believed, was nearly complete. Newton had explained motion and gravity, Maxwell had unified electricity and magnetism, thermodynamics had explained heat. The universe appeared to be an elegant machine, its cogs and wheels governed by precise mathematical rules. There were, as one physicist famously remarked, only a few small clouds left on the horizon. Yet it was in those clouds that the storm of the 20th century was waiting to be born. One of those clouds was the problem of blackbody radiation, how objects emit light when heated. Every physicist in Europe was aware of it, and many had tried to solve it. When a piece of metal was heated, it glowed red, then orange, then white. The pattern of light it emitted could be measured, and experiments showed a curve that classical theory could not explain. According to the equations of the time, an object should radiate infinite energy at high frequencies, an absurd prediction known as the ultraviolet catastrophe. Nature, clearly, was not behaving as physics demanded. Planck approached this problem not as a rebel, but as a mathematician. He was deeply conservative, a believer in the continuity of natural laws. To him, energy was like water, it could flow in any amount, smoothly and infinitely divisible. Yet every formula he wrote betrayed that belief. The numbers diverged, the results exploded into infinities. Something was wrong at the very foundation. Each evening, as the light in his Berlin study faded, Planck would sit alone, surrounded by silence and thought. He was a man of discipline, shaped by the traditions of German academia and a lifelong belief in the order of the cosmos. But the equations he faced were merciless. The experimental data from physicists like Lummer and Pringsheim, who had meticulously measured radiation spectra, did not fit any classical theory. Planck felt trapped between conviction and evidence, a scientist forced to confront the limits of his own understanding. In desperation, he began to play with mathematics that went against his instincts. To make the data fit, he assumed, almost reluctantly, that energy could not vary continuously, but must come in small, fixed packets. Each packet's size depended on the frequency of the radiation. This assumption was so foreign to his thinking that he treated it as a temporary trick, a mere mathematical device to make the curve align with reality. And yet, when he plotted the result, it matched the experimental data perfectly. Against all his expectations, nature seemed to agree with this strange idea. It was the autumn of 1900 when Planck realized what he had stumbled upon. With trembling hands, He wrote in his notebook the formula that would later be called Planck's law, and in that formula was a new constant of nature, the quantum of action. It was a number that linked energy and frequency in a way no one had ever imagined. For every frequency of light, the energy it carried was not arbitrary but came in multiples of h tal f, where f was the frequency. It was as if energy itself had been carved into indivisible grains. The implications were staggering, though Planck himself did not yet grasp them fully. He had introduced something that defied centuries of physics, something that quietly dismantled the belief in a continuous, predictable universe. But in that moment, all he cared about was that the theory worked. It fit the experimental curve like a glove. He presented his results to the German Physical Society on December 14, 1900, in what would later be remembered as the birth of quantum theory. Few of his colleagues understood the depth of what he had done. To them, it was a minor correction to classical physics. To history, it was the first crack in the wall of determinism. Planck himself did not think of it as a revolution. He was cautious, even skeptical of his own discovery. An act of desperation, he would later call it. He believed that somehow, future refinements of classical theory would make his discrete energy packets unnecessary. But the universe had no intention of returning to classical simplicity. Within a few years, other minds would take Planck's hesitant step and turn it into a bold leap into the quantum world. But for now, in the quiet of his study, Planck was left alone with his equations and his doubts. He could not ignore the philosophical weight of what he had done. If energy was quantized, then perhaps nature itself was not continuous. Perhaps the very foundation of reality came in steps, not flows. To a man trained to see harmony in the universe, this was a deeply unsettling thought, and yet there was also beauty in it, a new kind of order hidden within the apparent chaos. The story of Planck's discovery is often told as a moment of genius, but it was also a story of perseverance, humility, and inner conflict. He was not chasing glory, he was simply following the truth, wherever it led. His calculations were rooted in careful observation, not bold speculation. And yet, by trusting the evidence over his intuition, he had stumbled upon a truth that would forever change the human understanding of the cosmos. As the 20th century dawned, few realized that Planck's simple constant would become the cornerstone of all modern physics. In those days, even Einstein was still an unknown patent clerk, and Niels Bohr was a student. The great edifice of quantum mechanics had yet to be built, but its foundation had been laid by a man who never sought to break the old laws, only to explain them more precisely. The years following Planck's discovery brought both recognition and reflection. He received the Nobel Prize in Physics in 1918 for his work on the quantum theory, but by then he had already lived through immense personal and societal turmoil. He watched his beloved Germany crumble under war, and he endured the loss of his children. Yet through all his suffering, his belief in the rationality of nature remained. Even when quantum theory evolved into something stranger than he had imagined, Planck continued to see it as a deeper expression of natural order. The scientific community, however, was divided. Some embraced the quantum idea with excitement, others resisted it with suspicion. The thought that energy, and perhaps reality itself, was discontinuous seemed absurd. The world, after all, appeared smooth and continuous to the human eye. Yet every experiment confirmed what Planck's equation had implied: nature, at its most fundamental level, operated in quanta. As more physicists examined the consequences of Planck's formula, the true depth of his discovery began to unfold. Light, electricity, magnetism, all behaved differently under the lens of quantum thinking. It was as if Planck had given scientists a key to a hidden dimension of the universe. But even as they turned the key, they found that each door opened only to reveal new mysteries. Planck's discovery did more than alter the equations of physics. It altered the philosophy of science itself. For centuries, scientists had believed in a deterministic universe, one where everything could be predicted if enough information were known. But quantum theory introduced a different vision, one where probability ruled, and certainty was replaced by likelihood. The very concept of causality was shaken, and yet Planck remained at his core a believer in order. He viewed his quantum as a bridge, not a break. To him, it was a refinement of classical physics, not its destruction. He once said, "A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die, and a new generation grows up that is familiar with it." He understood that revolutions in thought move slowly, not through argument, but through time. Outside the halls of academia, the implications of Planck's idea began to ripple through the world in unseen ways. The technologies of the future, lasers, computers, transistors, and atomic clocks, would all trace their lineage back to that moment in Berlin when a man chose to follow mathematics instead of convention. His quantum constant, once a curiosity, would become a universal language for describing everything from the glow of a star to the flicker of an atom. In retrospect, it is easy to see Planck's quantum idea as inevitable, but in his time, it was a leap into the unknown. It required courage to propose that the fabric of reality might be discrete, that the universe might operate in rhythms too subtle for classical reasoning. It was not the work of rebellion, but of faith in the power of reason, and in the idea that even when the universe seems irrational, there is logic hidden beneath its mysteries. As the world moved deeper into the 20th century, Planck's discovery would inspire a generation of scientists, Einstein, Bohr, Schrödinger, Heisenberg, to explore the strange consequences of the quantum world. They would find that reality itself behaved not as a machine, but as a symphony of probabilities, where observation and existence intertwined in ways no one could have imagined. But all of that began with one man's persistence, a man who refused to look away from a problem that didn't fit the rules. The revolutionary quantum idea was not born from chaos or ambition. It was born from necessity, from the stubborn refusal of nature to conform to human expectation. And in that refusal, Planck found beauty. He once wrote, "Science cannot solve the ultimate mystery of nature. That is because, in the final analysis, we ourselves are part of nature, and therefore part of the mystery that we are trying to solve." He had glimpsed something profound, that the search for knowledge is not just about uncovering laws, but about understanding our place within them. His quantum was more than a constant. It was a statement about the limits of human understanding and about the infinite depth of the universe. In the glow of his discovery, a new era of science began to dawn. The classical world of certainty faded, and in its place rose a universe woven from quanta, discrete, unpredictable, yet exquisitely ordered. Max Planck had not just solved a problem, he had redefined what it meant to know. The dawn of the 20th century was unlike any other in the history of science. Something subtle yet irreversible had shifted. A single equation, born in the quiet of Max Planck's Berlin study, had opened a fissure in the foundations of classical thought. At first, no one could see how deep that fissure ran. To most physicists, Planck's idea of quantized energy was merely a convenient mathematical device, a patch to fix a leaky theory. But the universe had other plans, and through that small mathematical doorway poured an entirely new vision of reality. In the years following Planck's presentation to the German Physical Society, the community of physicists continued to wrestle with his formula. Some admired its precision, others dismissed it as an ad hoc contrivance. Planck himself remained cautious, even apologetic, as though he had violated some sacred law of continuity. He wrote privately that he had been forced to assume energy came in discrete quanta, for lack of a better solution. Yet the experimental results refused to be ignored. The data aligned perfectly with his theory, and each new experiment reaffirmed what his mathematics foretold. Something fundamental in nature was granular. Across Europe, young physicists began to notice. Among them was a 26-year-old patent clerk in Bern, Albert Einstein, whose restless imagination would soon take Planck's modest hypothesis and ignite it into a full-blown revolution. Einstein saw in Planck's equation not just a mathematical trick, but a description of reality. If energy was emitted and absorbed in packets, he reasoned, perhaps light itself was made of those packets, tiny quanta of energy he called liquantum. With that bold thought, Einstein explained the photoelectric effect, showing that when light struck a metal surface, it could eject electrons only if its quanta carried enough energy. No amount of weak light, no matter how intense, could do what a single high-frequency quantum could. This was the first real proof that energy was not continuous, and it transformed Planck's desperate assumption into a universal principle. Planck at first was uneasy about Einstein's interpretation. He had quantized the emission of energy, not the light itself. But Einstein's success in explaining the photoelectric effect, and later, the specific heat of solids, made it impossible to dismiss the quantum as mere abstraction. Gradually, Planck began to accept that the world was built from discrete exchanges of energy. His constant H became the heartbeat of the microscopic world, linking energy to frequency in every process, from the glow of stars to the vibrations of atoms. The quantum, once a reluctant compromise, was turning into the language of the cosmos. Yet even as these insights spread, the philosophical unease grew. If light could behave like a stream of particles, what happened to the beautiful wave equations of Maxwell? Could both pictures be true? Planck's work had not destroyed the wave theory, it had complicated it beyond recognition. In lecture halls from Cambridge to Copenhagen, physicists argued about whether light was a wave, a particle, or something stranger still. The lines that had once separated phenomena were dissolving. Every new experiment seemed to blur them further. By the 1910s, the ripple effect of Planck's idea reached the atomic scale. The Danish physicist Niels Bohr, inspired by Planck and Einstein, proposed that electrons orbit the nucleus in discrete energy levels. They could jump between orbits only by absorbing or emitting whole quanta of energy, each transition corresponding exactly to the frequency of light observed in spectral lines. For the first time, Planck's constant appeared not just in radiation formulas, but in the architecture of matter itself. Atoms, the very building blocks of reality, were quantum machines. This was a turning point that even Planck could scarcely have imagined. What had started as an effort to explain the color of glowing metal now reached deep into the structure of the universe. Quantum thinking was expanding, and with it came a new sense of wonder and discomfort. The neat, predictable world of Newton was dissolving into one ruled by probability and chance. Where Planck had sought order, the next generation found uncertainty. Still, Planck never abandoned his faith in the rationality of nature. He continued to teach, to write, and to defend the notion that the universe ultimately made sense, even if human comprehension had not yet caught up. To his students, he seemed both a father figure and a philosopher. Calm amid the storm of debate he had unwittingly unleashed. When younger physicists such as Werner Heisenberg and Erwin began formulating quantum mechanics in the 1920s, Planck watched with a mixture of pride and perplexity. Their mathematics was more radical than anything he had imagined. Heisenberg's uncertainty principle and Schrödinger's wave equation took the quantum idea and transformed it into a complete, self-consistent theory. But they also severed the last ties to classical intuition. Reality, they showed, was not deterministic but probabilistic. Particles did not have definite positions or paths until measured. The act of observation itself shaped the outcome. Planck admired their brilliance, but struggled with the philosophical implications. He had introduced quanta as a practical measure, they had turned it into a metaphysical revolution. When Einstein famously declared, "God does not play dice with the universe," Planck sympathized. He too hoped for a deeper harmony beneath the statistical surface. Yet he could not deny that the quantum formalism worked. Every experiment confirmed it, and every attempt to return to classical certainty failed. His constant H had become the bridge between the seen and the unseen, the measure of nature's smallest actions, the rhythm to which every atom danced. As the decades passed, Planck's discovery reshaped not only physics but technology and philosophy. Out of his equation emerged the foundations of the modern world: semiconductors, lasers, nuclear energy, quantum computing. Each device, each innovation, carries the imprint of that single constant, translating abstract theory into tangible power. When light beams through optical fibers, when electrons race through circuits, when atomic clocks measure time to trillionths of a second, Planck's quantum is at work, unseen yet omnipresent, a silent architect of precision. But behind the triumph lay a story of human endurance. Planck's life, like his science, was marked by both order and tragedy. He endured 2 world wars, the loss of his son in a failed coup against tyranny, the destruction of his home, and the erosion of the Germany he had loved. Through all of it, he clung to his belief in truth. He once wrote that science is the progress of human knowledge toward God, a statement that revealed both his humility and his awe. For him, understanding the universe was not about conquering it, but about participating in its mystery. When he looked back on his quantum discovery in his later years, Planck regarded it not as a personal triumph, but as a gift from nature, something revealed through persistence rather than brilliance. He never saw himself as the destroyer of classical physics. He saw himself as its continuer, extending its reach into the microscopic realm where new laws awaited. His work, he said, showed that even the smallest actions of the universe are quantized, and that beneath apparent chaos lies an unbroken order. In that quiet statement rests the essence of Planck's legacy. The quantum idea did not end with him. It spread like ripples on a still pond, shaping every subsequent discovery. When scientists later probed the nucleus, split the atom, and explored the realm of quantum fields, they found Planck's constant everywhere, an unchanging signature in the equations that govern all things. Even in cosmology, where physicists attempt to describe the birth of the universe itself, H appears as a reminder that creation unfolds in discrete steps. The Big Bang, the expansion of space, the flicker of virtual particles, all echo the same principle Planck uncovered while studying the glow of hot metal. There is a poetic symmetry to this, the smallest insight illuminating the largest questions. Planck's quantum idea, born from a practical puzzle, became the key to understanding stars, galaxies, and the very origin of time. It revealed that the universe is not a smooth continuum, but a mosaic of interactions, each governed by the tiny grain of action he discovered. Every photon that travels across the cosmos carries with it the imprint of H, a whisper from the moment when energy first became quantized. And so the story circles back to that night in 1900, when Planck adjusted his equations one last time and realized he had found the curve that fit the data. He could not have known that he was rewriting the script of reality. He could not have foreseen that his constant would appear in every branch of physics, from thermodynamics to quantum gravity. He only knew that his work had brought theory and observation into harmony. In that harmony lay the seed of an intellectual transformation that would redefine humanity's relationship with nature. Today, more than a century later, the quantum world still astonishes. Physicists continue to wrestle with the meaning of measurement, superposition, and entanglement, concepts that trace their lineage directly to Planck's first step. Quantum mechanics remains both the most accurate and the most mysterious theory ever devised. Its predictions are confirmed to astonishing precision, yet its interpretation still defies intuition. Planck's discovery did not simplify the universe, it revealed its complexity in exquisite detail. In classrooms and laboratories across the world, Planck's name endures, not as a monument to certainty but as a symbol of curiosity. His story reminds us that science advances not only through brilliance but through perseverance, through the willingness to question even the most trusted assumptions. He taught that the universe speaks in patterns, and that those patterns may be stranger than imagination but never less beautiful. In the quiet of thought, one can almost hear the echo of that revelation. Energy comes not in continuous streams but in steps, in quanta. It is a rhythm written into the heart of existence, the pulse of creation itself. Every atom, every spark, every heartbeat follows that rhythm. And though Planck sought only to understand a simple curve of radiation, what he found was the language by which the cosmos sings. Max Planck's revolutionary quantum idea was not just a turning point in science. It was a turning point in the human story. It showed that knowledge is never complete, that truth reveals itself layer by layer, and that sometimes the greatest discoveries arise from the quietest minds. In the flicker of heat and light, Planck had glimpsed the architecture of reality, and with that glimpse, he gave humanity a new way to see the world, not as a continuous expanse, but as a universe of countless tiny miracles, each one measured by the same constant heartbeat of creation. In the years following Planck's discovery, the world of physics found itself standing before an unfamiliar frontier. The equations that had once described the universe with comforting precision were now riddled with mysteries. The classical laws of motion and energy, those elegant principles of Newton and Maxwell, had carried humanity from the age of steam to the dawn of electricity. But suddenly they seemed incomplete. Something deeper was stirring beneath the surface of matter, a hidden logic that refused to fit within the boundaries of old theories. In laboratories across Europe, young physicists were listening to that new rhythm of nature, trying to translate its strange and beautiful language. The birth of quantum physics was not a single moment of revelation, but a gradual awakening. Planck had lit the first spark, and now it began to spread through minds eager to understand what is constant truly meant. Each experiment, whether it involved glowing metals, the photoelectric effect, or atomic spectra, seemed to whisper the same secret: nature does not flow smoothly. It moves in jumps, in sudden transitions, in packets of action. This was more than a new idea, it was the beginning of a new reality. In this atmosphere of uncertainty, the next generation took up the challenge. Niels Bohr, a quiet but daring thinker from Denmark, looked at the puzzle of the atom and found in Planck's quantum a guiding light. He imagined electrons circling the nucleus not as continuous paths but as quantized orbits. They could leap from one orbit to another only by absorbing or releasing fixed amounts of energy, each leap corresponding to a specific frequency of light. It was a breathtakingly simple picture, and yet it explained the mysterious colors of hydrogen's spectrum that had defied classical theory for decades. For the first time, the microscopic world made sense, though in a way that defied intuition. When Bohr unveiled his atomic model in 1913, the physics community was divided. To some, it was a masterpiece of logic, to others it was heresy against common sense. But slowly, as more evidence accumulated, Bohr's theory gained ground. The quantum was no longer just a mathematical device, it was becoming a fundamental principle. What began as a correction to blackbody radiation had evolved into a description of how atoms themselves behaved. A new branch of physics had been born, one that no longer obeyed the rules of the macroscopic world. The consequences were profound. In this new physics, certainty was replaced by probability, continuity by discreteness, and determinism by chance. The universe, once seen as a clockwork machine, now appeared alive with unpredictability. For some, this was exhilarating, for others, deeply unsettling. Einstein admired the precision of quantum theory, but refused to accept its randomness. God does not play dice, he said, unwilling to believe that nature's laws could be governed by probability. Yet experiment after experiment confirmed that the dice were indeed being thrown, and that the outcomes followed Planck's tiny constant like notes in a cosmic symphony. Through the 1920s, the young rebels of physics transformed this strange idea into a rigorous framework. Werner Heisenberg, working in the small island town of Helgoland, developed matrix mechanics, a mathematical language that described the quantum jumps between atomic states. Around the same time, Erwin, inspired by waves rather than matrices, formulated an equation that portrayed matter itself as a wave of probability. The two approaches, though different in form, described the same reality. Out of their union came quantum mechanics, a theory that could predict with astonishing accuracy how particles behave interact, and transform. This was not merely an improvement on classical physics. It was a complete reimagining of nature. The quantum world did not obey the same logic as the everyday world. Particles could exist in multiple states at once. They could interfere like waves, yet strike detectors as single points. Their exact positions and momenta could never be known simultaneously, a truth expressed in Heisenberg's uncertainty principle. Observation itself became part of the story, an act that shaped what was observed. To enter the quantum realm was to accept that reality is not fixed but fluid, not absolute but relational. And yet, despite its strangeness, this new physics worked. It explained the stability of atoms, the colors of light, the behavior of electrons, and the structure of matter. It became the foundation upon which all modern technology would later be built. But in those early years, its pioneers were not thinking of computers or lasers. They were simply trying to make sense of a universe that had become infinitely more mysterious. Their debates filled lecture halls and cafes, their letters pulsed with excitement and confusion. Out of their arguments emerged a deeper truth. The universe was not designed to be simple. It was designed to be understood through curiosity, persistence, and imagination. Max Planck, now an elder statesman of science, watched this revolution unfold with mixed emotions. He admired the brilliance of the younger generation, but worried about the philosophical implications of their theories. He had introduced the quantum as a practical necessity, not as a fundamental law of existence. Yet he could not deny that their discoveries grew naturally from his own. The seed he had planted had blossomed into a forest of new ideas, each one challenging the boundaries of human thought. As the new century advanced, the influence of quantum theory spread far beyond physics. Philosophers, artists, and thinkers began to draw inspiration from its paradoxes. The idea that reality could exist in multiple possibilities until observed echoed in literature and art. The notion of uncertainty mirrored the modern human condition, a world shaken by change, innovation, and war. The quantum revolution had not only altered the way scientists saw nature, it had transformed the way humanity saw itself. From the ashes of classical certainty rose a new understanding that mystery is not the enemy of knowledge, but its companion. Quantum physics taught that even in the smallest details of the universe, there lies a rhythm of wonder, a balance between order and chaos, between what we can measure and what we can only imagine. It reminded humanity that knowledge has no final destination, only endless horizons. In that realization, the new branch of physics became more than a scientific discipline. It became a testament to the human spirit. Born from doubt, nurtured by courage, and sustained by curiosity, it proved that even the most established truths could give way to deeper insight. From Planck's cautious calculations to Bohr's daring leaps, from Heisenberg's uncertainty to Schrödinger's waves, the quantum idea had evolved into a living story, a story still being written, particle by particle, question by question, through the hands and minds of those who dare to ask how reality truly works. As the 20th century unfolded, the quiet revolution sparked by Planck's discovery gained momentum, carried forward by a generation of brilliant and daring minds. These were not merely scientists, they were explorers navigating a terrain that defied logic, intuition, and even the very laws that had guided humanity's understanding for centuries. Each of them approached the mysteries of the quantum world with a mixture of curiosity, courage, and humility, fully aware that they were charting a path no one had walked before. Niels Bohr, the Danish physicist, became one of the first to breathe life into Planck's abstract ideas. He turned the quantum into a tangible concept by imagining electrons orbiting the nucleus in precise, discrete levels. It was an audacious leap, one that transformed the understanding of the atom from a vague notion into a structured, quantifiable system. Bohr's model explained phenomena that had baffled physicists for decades, such as the discrete spectral lines of hydrogen. Yet it was more than a technical breakthrough, it was a philosophical shift. Bohr's atom revealed that the microscopic world obeyed rules that were fundamentally different from the macroscopic universe humans experienced. Across Europe, a younger generation of physicists began to wrestle with these rules, pushing the quantum concept into uncharted territories. Werner Heisenberg, a prodigy from Germany, embraced abstraction to capture the behavior of particles. He developed matrix mechanics, a mathematical framework that described the transitions of electrons between energy levels without needing to define their exact paths. In Heisenberg's world, particles existed not as tiny billiard balls moving predictably, but as entities defined by probabilities, their characteristics only emerging through interaction with measuring instruments. This was a radical departure from classical determinism, a clear sign that reality at its most fundamental level was stranger than anyone had imagined. Meanwhile, in Zurich, Erwin sought a more visual, intuitive understanding of the quantum universe. Inspired by the idea of waves, he formulated his wave equation, which described electrons as wave functions spreading through space. Schrödinger's approach offered a complementary perspective to Heisenberg's abstract matrices, providing insight into the probabilistic nature of particles while retaining a sense of continuity and elegance. Together, the two frameworks, matrix mechanics and wave mechanics, painted a more complete picture of the quantum world, demonstrating that the same phenomena could be understood in multiple, equally valid ways. These pioneers faced resistance, not only from older scientists wedded to classical physics, but also from the limits of human intuition itself. The quantum realm behaved in ways that seemed contradictory to everyday experience: particles that acted like waves, waves that collapsed into discrete events upon observation, and uncertainty that defied the desire for exact measurement. Philosophers and physicists alike struggled to reconcile these contradictions. Einstein, while celebrating the precision and predictive power of quantum mechanics, famously rejected its reliance on probability, insisting that God does not play dice with the universe. Yet even he was forced to acknowledge that, despite its philosophical discomfort, quantum theory accurately described the behavior of the microscopic world. The collaboration and debate among these pioneers were as crucial as their individual discoveries. Niels Bohr's Institute in Copenhagen became a hub for discussion, where young scientists challenged each other, tested assumptions, and refined ideas. In these intense exchanges, the principles of quantum mechanics were not merely learned. They were lived, argued over, and deeply questioned. Concepts like complementarity, superposition, and uncertainty were forged in conversation and controversy, shaping the intellectual culture of an entire generation. Marie Curie, though working primarily in radioactivity, also played a significant role in demonstrating the realities of energy, quanta, and atomic transitions. Her meticulous experiments with radioactive substances provided empirical support for the notion that energy is emitted in discrete amounts. Curie's work exemplified the interplay between theory and experiment that defined the era. While theorists developed new mathematical frameworks, experimentalists confirmed or challenged these ideas through painstaking observation. Max Born, a contemporary of Heisenberg and Schrödinger, introduced the statistical interpretation of the wave function, asserting that the square of the wave function represented the probability of finding a particle in a given location. This interpretation transformed the philosophical understanding of quantum mechanics, making probability a fundamental aspect of nature rather than a reflection of human ignorance. It was a radical shift in thinking, yet it provided a consistent and predictive framework for experiments, cementing the role of the pioneers as architects of a new reality. The collective work of these scientists reshaped humanity's view of the universe. What had once seemed predictable and continuous was now understood as discrete, probabilistic, and interconnected in ways that challenged intuition. Electrons could exist in superpositions, light could behave simultaneously as a particle and a wave, and observation itself became an act that influenced outcomes. The pioneers of quantum mechanics did more than discover laws. They revealed a deeper structure underlying all of existence, one that forced a reconsideration of what it meant to know, to measure, and to understand. Even as they constructed the theoretical edifice of quantum mechanics, these pioneers remained profoundly human. They argued, doubted, and sometimes disagreed fiercely, yet they shared a sense of wonder and responsibility. They understood that they were not merely cataloging facts, but uncovering principles that would shape technology, philosophy, and the very conception of reality for generations to come. Their discoveries laid the groundwork for nuclear physics, semiconductors, lasers, and, eventually, quantum computing. Every modern device that relies on the peculiarities of the microscopic world traces its origin to the insights of these men and women. The story of quantum pioneers also illustrates the power of collaboration and the cumulative nature of scientific discovery. Planck's initial hypothesis was a quiet act of necessity. Einstein's interpretation turned it into a bold declaration about light, and Bohr, Heisenberg, Schrödinger, Curie, and Born transformed it into a comprehensive theory that described the behavior of atoms and subatomic particles. Each built upon the work of the others, demonstrating that science advances not through solitary genius alone, but through dialogue, debate, and the relentless pursuit of understanding. By the late 1920s, quantum mechanics had matured into a formal theory, capable of making precise predictions about atomic and subatomic behavior. Yet its conceptual challenges persisted. Philosophical debates, thought experiments, and paradoxes continued to emerge, reminding humanity that understanding nature is not just about equations, but about grappling with its fundamental mysteries. The pioneers had created a framework that worked, but the deeper meaning of that framework, the why of quantum mechanics, remained elusive. Ultimately, the pioneers of quantum mechanics were guided by curiosity, rigor, and imagination. They were willing to abandon familiar intuitions, to follow evidence where it led, and to accept a universe far stranger than classical physics had prepared them for. Their work not only unlocked the secrets of the atom, but also redefined the relationship between humanity and nature. It showed that reality is not a static machine, but a dynamic interplay of possibilities, probabilities, and interactions, waiting to be explored with both mind and imagination. Through their discoveries, the quantum pioneers illuminated a path into the unknown. They revealed a universe in which certainty is limited, observation is participatory, and the smallest elements of existence obey rules that challenge perception. Their courage, creativity, and relentless curiosity created a legacy that endures in every corner of science and technology. In their hands, quantum mechanics became not just a branch of physics, but a new lens through which to view the cosmos, a lens that continues to inspire wonder, debate, and discovery to this very day. As the foundations of quantum mechanics solidified in the 1920s and 1930s, the implications of the theory extended far beyond laboratory experiments and mathematical equations. The quantum revolution did not merely reshape physics, it challenged humanity's most basic assumptions about reality, knowledge, and certainty. It forced scientists, philosophers, and the broader public to reconsider what it meant to observe, to measure, and to understand the natural world. What had begun with Planck's seemingly modest idea, that energy comes in discrete quanta, had grown into a paradigm shift, reshaping both science and thought. The impact on the scientific community was immediate and profound. Classical determinism, the belief that the universe operated like a predictable machine governed by unchanging laws, was shown to be incomplete. Heisenberg's uncertainty principle demonstrated that certain pairs of physical properties, such as position and momentum, could not be simultaneously known to arbitrary precision. This was not a flaw in measurement or technology, it was a fundamental property of nature itself. Reality, at the quantum level, is probabilistic, governed by likelihood rather than certainty. For scientists accustomed to the predictability of Newtonian mechanics, this was both thrilling and unsettling. Equally revolutionary was the idea of superposition. Schrödinger's wave mechanics revealed that particles could exist in multiple states simultaneously until observed, an idea famously illustrated in his thought experiment with a cat, simultaneously alive and dead in a sealed box. The paradox was intended to provoke reflection, highlighting the strangeness and counterintuitive nature of quantum mechanics. Yet it also underscored a profound truth: the act of observation is not passive, it is an interaction that shapes reality. The observer and the observed are inextricably linked, dissolving the classical boundary between subject and object. The philosophical ramifications of quantum mechanics rippled through intellectual circles. It challenged materialist and deterministic worldviews, suggesting that uncertainty and probability are intrinsic aspects of the universe. This raised profound questions about causality, free will, and the limits of human knowledge. If nature does not unfold according to absolute rules, then the role of the scientist is not to impose certainty, but to interpret probabilities and patterns. The quantum revolution, in essence, demanded a new humility, a recognition that reality is more complex and subtle than classical intuition allows. Einstein's resistance to certain interpretations of quantum mechanics exemplified the tension between empirical success and philosophical discomfort. While he acknowledged the theory's predictive power, he questioned its completeness. His famous remark, "God does not play dice with the universe," reflected his unease with the notion that chance governs fundamental events. Debates between Einstein and Niels Bohr, often conducted through letters and meetings at the Solvay conferences, epitomized the struggle to reconcile experimental results with human understanding. These discussions, however, did not undermine the validity of quantum mechanics. Instead, they deepened its conceptual richness and inspired generations of physicists to explore the philosophical dimensions of their work. The technological impact of quantum theory was equally transformative. Understanding the quantum nature of energy and matter enabled the development of semiconductors, lasers, and magnetic resonance imaging, all of which rely on principles first articulated by Planck, Bohr, and their successors. Quantum mechanics also laid the groundwork for nuclear physics, leading to both the destructive and constructive uses of atomic energy. What was once an abstract, mathematical framework became the foundation of technologies that define the modern world. The revolution was not merely conceptual, it was practical, influencing medicine, computing, telecommunications, and energy production in ways that early pioneers could scarcely have imagined. At the same time, quantum mechanics reshaped scientific methodology. It highlighted the importance of probabilistic models and statistical interpretation, encouraging scientists to embrace uncertainty as an inherent aspect of investigation. Max Born's interpretation of the wave function as a probability amplitude provided a consistent framework for predicting the behavior of particles, illustrating that prediction, rather than deterministic description, could be the goal of science. This philosophical shift redefined what it means to know in the natural sciences, establishing a new standard for rigor and conceptual sophistication. Beyond physics, the quantum revolution influenced broader culture and thought. Writers, artists, and philosophers drew inspiration from the counterintuitive principles of quantum mechanics. The idea that reality is probabilistic, interconnected, and observer-dependent resonated with modernist explorations of perception, consciousness, and uncertainty. Quantum mechanics, in this sense, became more than a scientific theory. It was a lens through which to examine the complexity and ambiguity of the human experience. It challenged people to see the world as fluid and dynamic, rather than fixed and absolute, and to embrace the mysterious as an essential aspect of existence. The pioneers of quantum mechanics, Planck, Einstein, Bohr, Heisenberg, Schrödinger, Born, and others, understood that their work represented both a triumph and a responsibility. They had glimpsed the underlying structure of reality, yet they also realized that understanding the consequences of their discoveries would take decades. Each experiment, each theoretical advance, revealed more of the hidden architecture of the universe, but also raised new questions. The quantum revolution was thus both a culmination and a beginning, a recognition that the pursuit of knowledge is never complete, and that the deeper one probes, the stranger the universe becomes. Quantum mechanics also transformed the educational and institutional landscape of physics. Universities and research institutes reorganized their curricula to include these revolutionary concepts, training a new generation of scientists capable of navigating the probabilistic, non-intuitive realm of the atom and the subatomic. Collaborative networks emerged, enabling rapid exchange of ideas, debate, and verification. The international scientific community became increasingly interconnected, and quantum theory served as a common language bridging nations, disciplines, and generations. In retrospect, the philosophical and scientific impact of the quantum revolution cannot be overstated. It challenged assumptions about causality, determinism, and objectivity, while providing an unprecedented predictive framework for understanding the microscopic world. It forced humanity to recognize the limits of intuition and the power of mathematics to reveal hidden truths. The quantum revolution was, in every sense, a transformation not only of physics but of human thought itself, a realization that reality is subtler, richer, and more intricate than anyone had imagined. Ultimately, the quantum revolution demonstrated that science is both an intellectual and a philosophical endeavor. It is not simply about accumulating facts or solving problems. It is about expanding the boundaries of what can be imagined, perceived, and understood. The pioneers of quantum mechanics showed that curiosity, rigorous thought, and the courage to challenge established norms can uncover truths that transform both knowledge and the world. From Planck's first quanta to the technologies and ideas that shaped the 21st century, the quantum revolution stands as a testament to human ingenuity, persistence, and wonder. It is a story of courage, collaboration, and intellectual daring, revealing that even the smallest insights, the quantization of energy, the jump between atomic levels, the probabilistic behavior of particles, can unleash a cascade of understanding that reshapes the entire landscape of human knowledge. The quantum revolution, born of Planck's initial discovery, continues to unfold, inspiring scientists and thinkers to explore, question, and embrace the strange, beautiful, and mysterious universe in which we live. The story of quantum mechanics did not end with its formal establishment in the early 20th century. Rather, it marked the beginning of a new era in which the boundaries of human knowledge would continue to expand. The discoveries of Planck, Bohr, Heisenberg, Schrödinger, Born, and their contemporaries created a framework that not only explained the microscopic behavior of matter, but also redefined the relationship between humanity and the universe. This legacy is more than a collection of equations or a set of experiments. It is a testament to the power of curiosity, imagination, and persistence. Even as quantum mechanics matured, its influence spread across science, philosophy, and technology. It transformed the study of atoms, molecules, and subatomic particles into a precise and predictive discipline, allowing scientists to probe realms once thought inaccessible. Nuclear physics, solid-state physics, and quantum field theory all emerged from the foundations laid by the early pioneers. The rules of quantization, probability, and uncertainty guided these fields, enabling discoveries that reshaped the very fabric of the natural world. Each new insight built upon the work of those who had first glimpsed the strange rhythm of quanta, demonstrating that science is an evolving conversation across generations. The practical applications of quantum mechanics soon became astonishingly tangible. Semiconductors, the building blocks of modern electronics, rely on principles of quantum behavior to control the flow of electrons. Lasers, whose precision and power have transformed medicine, industry, and communication, operate entirely on the principles of stimulated emission first understood through quantum theory. Magnetic resonance imaging, which allows doctors to peer inside the human body without surgery, is another direct consequence of the quantum understanding of nuclear spins. From computers to smartphones, from atomic clocks to GPS navigation, The technologies that define the contemporary world are built upon the insights of quantum pioneers. The universe's smallest rules became tools for shaping civilization in unprecedented ways. Yet beyond technology, the quantum revolution continues to inspire philosophical reflection. The probabilistic nature of reality challenges classical notions of causality and determinism. Superposition, entanglement, and observer-dependent phenomena prompt deep questions about the nature of knowledge and the limits of human perception. If particles can exist in multiple states simultaneously, if observation can influence outcomes, then the act of knowing becomes inseparable from the phenomena being observed. Quantum mechanics forces humanity to confront the delicate interplay between reality and understanding, a reminder that knowledge is not merely accumulation, but participation in the universe's unfolding mystery. The educational impact of quantum mechanics is profound. It has transformed curricula and research practices across the globe, training generations of scientists to think in terms of probabilities, wave functions, and quantized energy. Laboratory work, computational modeling, and theoretical analysis now coexist in a delicate balance, reflecting the dual nature of quantum phenomena themselves. Students of physics are no longer taught to see the universe as predictable and continuous. They are encouraged to explore uncertainty, embrace abstraction, and navigate complexity. This transformation in education reflects the lasting intellectual influence of the quantum revolution, shaping minds capable of confronting challenges as diverse as fundamental research, engineering, and emerging technologies. In addition, quantum mechanics has inspired new fields of inquiry that were unimaginable a century ago. Quantum computing, still in its developmental stages, promises to revolutionize information processing by exploiting superposition and entanglement. Quantum cryptography offers the potential for secure communication based on the inviolable principles of quantum physics. Quantum teleportation, once a fantastical idea, has been experimentally realized in laboratories, demonstrating that the strange principles of entanglement can be harnessed in practical ways. These advancements highlight the enduring vitality of Planck's initial insight, that energy is quantized, and the capacity of quantum principles to open doors to the previously impossible. Culturally and intellectually, quantum mechanics continues to shape our understanding of the universe and ourselves. Writers, philosophers, and artists have drawn inspiration from its counterintuitive principles, exploring themes of uncertainty, duality, and interconnectedness. The theory challenges not only scientific conventions but also human perceptions, reminding us that reality often defies expectation and imagination. By revealing the universe's subtle architecture, quantum mechanics encourages a humility that is both scientific and philosophical. The recognition that knowledge is provisional, observation is participatory, and the cosmos is infinitely more intricate than immediate appearances suggest. The legacy of quantum mechanics also underscores the collaborative nature of scientific discovery. Planck's initial breakthrough might have remained a minor correction to classical theory if not for the insights and persistence of Einstein, Bohr, Heisenberg, Schrödinger, Born, and countless others. Each added layers of understanding, tested, debated, and refined the implications of quanta, ultimately constructing a robust, predictive, and conceptually rich framework. The quantum revolution exemplifies how knowledge grows through dialogue, experimentation, and the courage to question deeply held assumptions, demonstrating that even the most abstract insights can transform reality when nurtured through collaboration and persistence. As the 21st century progresses, quantum mechanics remains a living, evolving field. Researchers continue to probe the behavior of particles, the nature of entanglement, and the limits of quantum computing. The search for a unified theory that reconciles quantum mechanics with general relativity, an elusive theory of everything, continues to challenge the brightest minds. Yet the principles established over a century ago remain central. Energy is quantized, uncertainty is fundamental, and observation is entwined with the phenomena observed. The quantum legacy is not frozen in time, It is an ongoing journey, a continuous expansion of understanding that both honors the past and anticipates the future. Perhaps the most enduring aspect of the quantum revolution is its ability to inspire awe. It reminds us that the universe is not merely a clockwork mechanism to be dissected and understood, but a dynamic, subtle, and interconnected system filled with surprises. It demonstrates that the pursuit of knowledge is not linear but exploratory, filled with unexpected turns and discoveries. The work of Planck and the pioneers shows that insight often arises from careful observation, persistent questioning, and the willingness to embrace ideas that initially seem paradoxical or uncomfortable. In the end, the legacy of quantum mechanics is both tangible and philosophical. It underpins the technologies that define modern life, informs the research that drives progress, and continues to challenge and expand human thought. It is a testament to the capacity of human curiosity, imagination, and rigor to uncover truths that transform our understanding of the cosmos. From the smallest particle to the structure of entire galaxies, the influence of Planck's initial insight continues to resonate, shaping the way humanity perceives and interacts with the universe. Quantum mechanics stands as a bridge between knowledge and mystery, a reminder that the journey of discovery is ongoing. The pioneers of the field showed that even a single insight, a quantized packet of energy, can ripple outward, generating waves of understanding that change science, technology, and philosophy forever. Their legacy endures in every experiment, every technological breakthrough, and every mind inspired by the strange and beautiful rules of the quantum world. It is a story of curiosity and courage, of questioning and perseverance, and above all, of the enduring human desire to comprehend the universe in all its complexity. Quantum mechanics is not merely a theory, it is a way of seeing, a lens through which the intricate, subtle, and wondrous nature of reality is revealed. It continues to guide, inspire, and challenge, a living monument to the brilliance of the minds who dared to see the world not as it seemed, but as it truly is, strange, elegant, and infinitely profound.